Hello students, welcome back. Let's go to section 3. Please be warned, this section starts off easy, but it gets really deep toward the end. Okay, that was a fair warning. Let's begin. Let's start with something simple. What do you mean by a homogeneous equation equal to 0? Non-homogeneous, non-zero, equal to something else, f of t. You can express the same thing using the linear differential operator expression. L of y is equal to 0, or L of y equals to f, like this, where L is given by this linear differential operator. By the way, I'm going to use this symbol quite often. Instead of writing just L of y equal to 0, I may write like this, using triple horizontal bar. What do you mean by this? It's a widely accepted notation. G is not just equal to 0, but like this, means G is constantly equal to 0. Constantly 0. That is, G of t is equal to 0 for all in the interval of definition. So whenever I write this triple horizontal bar, that means I'm emphasizing this part. For all t in the interval of definition. So g is equal to 0 for some t. In that case, we're gonna get what? Some y-intercept? That's not what you're looking for. Always equal to 0, constantly equal to 0. That's what this horizontal bar is talking about. And of course, that's what you're talking about for differential equation as well. So frequently, I'm gonna use these triple horizontal bar notation. And the emphasis is for all t in the interval of definition. Okay, that was a preparation. And let's go to 3.2, general solution theorem. Here we go. L of y is equal to 0 is a homogeneous linear ODE with order n. That is like this, of course. And then, of course, an, the leading coefficient, should not be constantly equal to 0. Otherwise, this is not going to be order n, because if it is constantly equal to 0, that drops out, then this entire thing will be order n minus 1 at the very most. So the leading coefficient is not always not equal to 0, so it is order n. Then this ODE has n linearly independent solutions, y1, y2, y3, and so on. Moreover, if there's any other solution, y, then that y can be written as a linear combination of those y1 through yn. So any solution can be written as a linear combination of y1, y2, y3, and so on. Let's come back to this theorem again. Part 1, they exist the linearly independent solutions, y1 through yn. The existence is part 1. Part 2, any solution will be written as a linear combination of y1 through yn. So this is the general solution. So the existence is part 1, and getting the general solution, that's part 2. Part 2, the generality part, is much harder to prove. So I'm going to revisit and do that in 3.6. Actually, the statement is the same here and there, except that I discussed only the first half here and the latter half over there. But before even starting the first half, let's discuss why we are doing this. Why in the world we are interested in this general solution theorem? Well, let me cook up a problem. So we have, let's see, 2, no, let's keep it simple. Monic plus 5y prime minus 6y is equal to 0. Okay, what do you have? We have a linear ODE with a constant coefficient. And how do you solve it? One way is to take the Laplace transform, and then you get R of S over Q of S and decompose by partial fraction. But let's suppose we are taking the substitution method. So we put y1 as, no, just y as e to the st like this. And then y prime is s times e to the st. Y double prime is s squared times e to the, like this, right? If you use the chain rule and put everything in there, then what you get? Y double prime is s squared e to, e to the st plus 5s e to the st minus 6 e to the st equal to 0. That's what you're getting. And then exponential is common, so divide everything by exponential. You can do it because exponential is never 0. Then what do you get? You get s squared plus 5s minus 6 is equal to 0. Alright, going good. S plus 5, s plus 6, s minus 1 is equal to 0. S is equal to negative 6, or s is positive 1. So we have these. Negative 6t. Y2 is e to the 1t. And then general solution can be written as c1 y1 plus c2. We can do it like this, and that's something we did for constant coefficient linear ODEs. I hope everybody remembers this. What did we use here? We used implicitly that we can find y1 and y2, two linearly independent solutions. Do they always exist? Actually, that's a question. Yes, indeed. That's why we can do it this way. Another thing, even more importantly, any solution can be written as a linear combination. So any solution can be written as a linear combination of c1y1 plus c2y2. Something we are going to prove here. We implicitly used it. Of course, if you use Laplace transform and then follow through, then you don't really have to go through these. Theoretically, everything is sound. But if you use substitution method, then actually you're leaving a lot of holes here and there, theoretically speaking. But the Laplace transform method is not going to work for the linear ODE with variable coefficients in general. So we'll have to do some other method, like the substitution method. In that case, we don't want to have a lot of holes lying around, especially considering that we are dealing with much harder problems. We are dealing with variable coefficient. So we want to have sound foundation. That's what this general solution theorem is taking care of. Yes, you can do that. y1 through yn exist. And yes, you can do that. The general solution is c1y1 plus c2y2 plus and so on. The latter part, the generality, is going to be much more difficult to prove, so let's postpone it. And here, let's prove the first half. All right. Here's a symbolic expression of the same thing. So solution y1 through yn exist. Those functions exist. And then L of y1, L of y2, all the way over to L of yn, they're all zeros, which means those are solutions. But not only that, they're solutions, yes, but not only that, they're linearly independent. Whenever you have linear combination equal to constantly 0, then all the coefficients must be 0. So we are going to be using ODEs. Ready to start proof? Okay, here we go. All right. Due to the fundamental theorem, L of y equal to 0 has a unique solution for each initial condition. Wait a minute, we are dealing with general solution here, so we do not have specified initial condition. Why are we considering initial condition here? Well, that's a punchline, as a matter of fact, and I'll show you what initial condition we are selecting in a moment. But for given initial solution, there's a unique solution. All right, y1, y2, y3, all the way over to yn are the unique solutions of, okay, here's a punchline. y1 is a unique solution of this initial value problem. ODE, and look at the initial condition here. Y of t0 is 1, and all the derivative, y prime of t0, y double prime, y triple prime, all those derivatives, all those 0. Look at y2, same ODE, but look at the IC. Where the first derivative is 1, everything else is all 0. Look at the third IC, same ODE, yes, but second derivative is 1, everything else is 0. And continue all the way over to last. Same ODE, all 0, but n minus first derivative, last derivative is 1. So we have n different initial conditions, same ODE, yes, but n differential initial conditions. So we have n different unique solutions, y1, y2, y3, all the way over to yn. That's the setting. And please pay attention to this IC, because we are going to be using it soon. So that's an ingenious trick, actually. Okay, here's the setup. Now, how do we prove that y1 through yn are linearly independent? They are solutions, yes. By the fundamental theorem, solutions exist. Fundamental theorem, it's here. Unique solution exists given initial condition. So we gave initial conditions like these. So we have unique solutions, y1 through yn, each for its own initial condition, okay? What's left is to prove that y1 through yn are linearly independent. That is, if I set up a linear combination equal to 0, I would like to prove that all the coefficients, c1, c2, c3, all of them is equal to 0. So that's what we have to prove. That is, we have to prove this. If the linear combination is equal to 0, then will all the coefficient be 0? That's what we want to prove. Okay? If the linear combination is 0, then all the coefficients, c1, c2, c3, all of them 0. That's what we want to prove. Of course, we don't have it yet. That's why I put question mark here, but that's where we are headed. We found out the candidate of the y1 through yn. They are here, the unique solutions of all these. Okay. All right, let's prove it. So we start with this linear combination, Okay, all right, let's begin. We start with this linear combination that's equal to 0. And that means it is constantly equal to 0, so I can plug in any t value. Which t value shall I select? I'm selecting t0. So directly plug in t0. Then, of course, equal to 0, because this is constantly equal to 0. I can plug in any number. I can put in t0, and of course equal to 0. But then again, what about all the others here? y2 of t0? That's 0, because y2 is a solution of the second equation here, second initial value problem. And the next, look at all this column here. They're all zeros. For y2, y3, y4, they're all zeros. Only this one is non-zero, and that's 1. So this is 1 and all 0. Conclusion, C1 has to be equal to 0. Alright, so this part just drops out, and C1 times 1 is equal to 0. C1 is equal to 0. So, alright, this one is 0, so dropped out. How about the next? From this linear combination, take the derivative. Take the derivative, c1y1 prime, c2y2 prime. In the end, we have cnyn prime. I took the derivative because I'm going to look at the second column now. Plug in t0 and y1, which is the solution of the first, that's 0. That's 0. And then plug in t0, so for the second initial value problem here, y2 prime, that's 1. You see, this is 1. That's 1. And then all the others, they're all zeros. Look at the second column. They're all zeros. Conclusion, that's 0. And all these 0. So C2 times 1 is 0. We get C2 equal to 0. Now it's clear, isn't it? Take another derivative, and then you're going to be looking at the third column here. And you're going to get y3 is equal to 0, which comes from the second derivative. That's 1, everything else is 0. Repeat it all the way to the last. Then what do you have? All these are zeros. They're all zeros. And then this green thingy, that's 1. So we have Cn equal to 0. Indeed, all the coefficients, C1, C2, C3, they're all zeros. That completes the proof. So what did you just establish? Whenever we have linear ODE with homogeneous linear ODE, homogeneous is important. There are n linearly independent solutions, y1 through yn. Now, do you have to find those y1 through yn by those particular initial conditions? No, you don't have to. No, you don't have to. But in any case, they exist. Linearly independent solutions exist. If you understand the linear algebra, then once you have those linear independence family there, then that will soon give rise to the concept of dimensions and so on. But you don't really have to know all those. I just want to find out the existence of linearly independent solutions, and we just proved it. So in the previous example, I showed you about this the linear equation, homogeneous linear equation of constant coefficients. I just assumed the linear independent solutions existed, and then I did some substitutions, didn't I? And that's because I knew already in advance, because it's a proven fact. Okay, I'll stop here, and then we'll continue over.